Okay, so for the people that weren't here yesterday and for the video that I did take yesterday, what we looked at, we talked about the difference between ionic and covalent bonding. We looked at how electronegativities of a atom, the higher the electronegativity is, the higher that pull for electrons. So an atom like fluorine really wants electrons, and an atom like francium just wants to get rid of them. And so the differences between these electronegativities kind of accounts for our ionic and covalent bonding. This whole unit is mostly focused on covalent bonding or molecular bonding. And so what we started looking at yesterday was Lewis dot symbols for different elements. And so, for example, if I want to do the Lewis dot diagram for, let's go with fluorine. So to do a Lewis dot diagram, we start with our atomic symbol. We put our atomic symbol in the middle, fluorine. And then I need to figure out how many valence electrons there are. And so in chlorine, it's in group 17. So how many valence electrons? 7. So 7 valence electrons. And then we have to remember how we fill in the valences. So when you fill in the valences, you're going to start at 12. So there's technically orbitals. So if this is my nucleus, there's orbitals at 12, 3, 6, and 9. And in each orbital, I can have how many electrons? 0, 1, or 2, right? Each orbital could have 0 electrons, 1 electrons, or 2 electrons. When I fill orbitals, I start at 12, and then I fill them one at a time around. So if I'm looking at drawing this Lewis dot diagram for chlorine, what I'm going to do is I put 1 electron, so 1, 2, 3, 4, 5, 6, 7. So that would be my Lewis dot diagram for chlorine. And it matters where you put these. You have to make sure you start at 12 and fill clockwise one at a time. Otherwise, your dot diagram will be incomplete, which then extends into 3D shapes. Obviously, you can't really mess up the shape of chlorine, whether there's 1 valence electron here or wherever, it's not going to matter. But for something like oxygen, for example, oxygen is in group 16, so it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. And what we talked about yesterday is we gave names to these different types of orbitals. So this orbital here and this orbital here are called what? Lone pairs. Those are orbitals that do not need any more electrons. They're happy. These ones right over here then are called what? Bonding electrons. And so this is where we could form a covalent bond by sharing electrons with another atom in order to satisfy what we call the octet rule. And the octet rule means what? There's 8, right? Every atom, with the exception of hydrogen and helium that we look at, is striving to get 8 electrons in their valence. So whether they've gained, lost, or shared, they want to reach 8 electrons. Is that okay? Everybody's okay with that from yesterday? People that missed? We'll see how it goes. Okay. All right, so what we're doing today is we're taking this a step further, and we are going to create molecular compounds with these Lewis dot diagrams. I think in your notes it says elements, so I kind of messed up on that. So electron dot diagrams used to show molecular compounds are called Lewis structures. So if it's just a single element, it's called a Lewis dot. If it's a compound, it's called a Lewis structure. Nomenclature doesn't really matter. So the big thing to know is that we are looking for those valence electrons to satisfy the octet rule. Each element wants access to 8 electrons, with the exception of hydrogen, which just wants 2 electrons. Electrons that are shared end up, we would call those bonding electrons. Once they're shared between 2 atoms, they then become called a bonding pair. And the sharing of 2 or 3 electrons between an atom can result in multiple bonds. So if two molecules are sharing more than just one set of electrons, they're sharing two or they're sharing three sets of electrons so that they satisfy their octet, we can have multiple bonds, not just what we call a single bond, but a double and a triple bond. Alright, so here's how we are going to draw these molecular compounds. So you draw the electron dot diagram for every element involved. So if I have, let's say, H2O, I'm going to draw the electron dot diagram for two hydrogens and an oxygen. And pretty much the key step here is place the atom with the most bonding electrons in the center. So whoever has the most bonding electrons is going to go as the center part of my molecule. Now, as we kind of go further into this unit, you kind of have to play around with that rule. But that's usually going to be the central electron, and then we're going to bond electrons around whatever that central atom is that has the highest bonding capacity. And then what you're going to do from there is arrange all other atoms as symmetrically as possible. So if I put one at 12, I want to put the other one at another one at 6, if I can. It depends on how the dot diagram works. And the last thing you want to do before you're like, okay, that's going to be what the 3D structure would look like, or how it would share those bonds, you have to make sure that every atom in there has the amount of electrons it wants. So it needs to have that satisfied octet. Okay, so let's just take a quick look at each of these, and this will kind of give me an example of what electrons are going to go in the center. So carbon has 4 valence electrons. Remember, carbon looks like this. How many valence electrons then does carbon have? Or sorry, how many bonding electrons? 4. So its bonding capacity is 4. Nitrogen, I gotta change my color here. Nitrogen has 5 valence electrons. So if I do my Lewis dot diagram for nitrogen, it's 1, 2, 3, 4, 5. So how many bonding electrons then for nitrogen? 3. And so the bonding capacity is also 3. Oxygen, I just drew on the last page there. Oxygen is 1, 2, 3, 4, 5, 6. So the bonding electrons, number of bonding electrons in oxygen, 2. What the heck happened there? And therefore the bonding capacity is 2. Any halogen, so anything in group 17, so for example, let's look at chlorine, has 7 valence electrons, so 1, 2, 3, 4, 5, 6, 7. What's its bonding capacity then? 1, 1. And hydrogen has 1 electron, which means it can form how many pairs? 1, right? Because when I do hydrogen, it just has the 1 electron, and it only has an orbital that can include 2 electrons. So this has a bonding capacity of 1. So, based off of this, if you were given all of these electrons in one molecule, which one would you place in the center? One with the highest bonding capacity, which is what? Carbon, right? Generally, if we see carbon in our molecular formula, that's always a starting point. If you see multiple carbons, you should add them together in a carbon chain. Okay, so let's look at a few examples here. So let's take a look at water here first of all. Okay, so if you want to do this first step, that's fine, but I generally don't do it, but you can. So the first step on the other page says write out the Lewis dot diagram for each of these. I'm just going to ignore these guys for now. So hydrogen looks like this. There's a hydrogen. Hydrogen looks like this, and oxygen. Now, usually when I'm drawing my Lewis dot diagrams, for every type of atom, I draw my electrons a little bit differently, because then I can keep, I can kind of account for what came from where. So then I'm going to say, okay, the oxygen has 6 valence electrons, so it's 1, 2, 3, 4, 5, 6. Okay, so then the next step we said was to put the atom with the highest valence or the highest bonding capacity in the middle. So what's going to go in the middle? oxygen. So I'm just going to rewrite this. So oxygen and then I want to bond on the rest of the molecules. So I can add this hydrogen in where? On the left side, so I'll put it right here. So hydrogen. And this guy is going to come here. So hydrogen. So there is my Lewis structure for water. The other thing I want to do is check that hydrogen and their oxygen's octets are satisfied. So if I look at this, hydrogen has hydrogen here has access to 2 electrons, that's good. This hydrogen has access to 2 electrons, that's good. And this oxygen has access to 8 electrons, so that's good. And that means that the octet for each of those elements involved is satisfied. And that's why that's a stable structure. Can I erase all that? Should I do one more and then you can do this one, or do one more? This one's harder. Yeah, this one's actually harder than this one. So I'll do 3 here. So CH3OH. So this here, when it gives me this little OH on the end, that's actually telling me this is a functional group. You'll learn more about functional groups in Chem 30. But that's just saying that there's going to be an oxygen attached to a hydrogen in that structure when they write it like that. Rather than them saying CH4O, they write it like this on purpose so you can kind of see that there's going to be that OH structure attached to each other. I usually choose not to write out, okay, carbon looks like this, and I have 4 hydrogens. I'm not going to do that. If I look at these, out of all of these, carbon, hydrogen, oxygen, what has the highest bonding capacity? Carbon. So I'm going to put my carbon molecule in the center. So 1, 2, 3, 4. It has a bonding capacity of 4. And then what I want to do from there is I'm going to bond on the hydrogens as symmetrically as possible. So I'm going to bond in these hydrogens right here. So 1 hydrogen, 2 hydrogens, 3 hydrogens. Now it's not, I went the top and the bottom and then the left. It's sort of symmetrical. And then I have to add in this OH. Why would I not put this hydrogen here? Pardon me? It's attached to the oxygen, and why can I not attach anything else to there? Right, if I add something attached to this hydrogen, well, then I violated the octet rule for hydrogen. And so what's going to bond in this orbital on the right here? The oxygen, right? So then oxygen has 1, 2, 3, 4, 5, and then the other oxygen bonded in right there. And last of all, I'm going to bond in the hydrogen at this 1 lone bonding capacity. So right here. That was the only space left for me to add in that hydrogen. And adding that hydrogen in there also satisfies my octet rule. So if I look at each of these, this hydrogen's octet rule is satisfied. This hydrogen's octet rule is satisfied. What the heck does that keep doing that for? That hydrogen's octet rule is satisfied. This carbon has access to 8 electrons, so that's good. This oxygen has access to 8 electrons, that's good. And this one is hydrogen is good. Sometimes people would make an error, and so sometimes people make an error and bond in hydrogen over here. Why is that incorrect? Well, it's still, this is 2, I'm good, right? But why would that be incorrect? Does anybody know? Right, the way oxygen is structured, it has to have 1, 2, 3, 4, 5, 6. So I have to form a bond here and a bond here, right? I can't form bonds like 180 degrees, like across from each other. That's not how the 3D structure of oxygen works. And so if you're putting it over here, that would be incorrect. You have to make sure you're doing your Lewis dot diagram appropriately. All right, so try then, oops, sorry. Try this one on your own, number 2. Give you a minute. Yep. Got it? Want me to check it? There, and you maybe print off more pool packages yesterday when you lost it already. Everybody think they got it? No? Pardon me? Oh, okay, yeah. I know why not. Guess I didn't do an example. Okay, let me show you how this one works. Oh, where's my pen? Okay, so this one, CH2O, so a carbon, 2 hydrogens, and an oxygen. So what did you guys start off with as your central atom? Carbon. Okay, so I'll put carbon in the center, and carbon has 1, 2, 3, 4. Okay, what's the next thing you tried to attach? Hydrogens. So when you add your hydrogens, if I add a hydrogen in at the top, I need to put the other one where? On the bottom, right? I want to kind of go as symmetrically as possible, so there's that one. All right, and then the next part, it's okay, because really, like, in a 3D space, it would maybe adjust itself, but that's fine. The next thing you would have done is try and add on the oxygen. So if I put my oxygen, now it doesn't matter where I put it, I'm going to put it here. So oxygen goes here, and it has these 6 valence electrons. Now, did everybody get that far? Okay, and then you're like, now what? Was that right? Okay, so what the problem is here for everybody is, well, if I look at this, my octet rules aren't satisfied, right? Like, carbon only has access to 7, and so does this oxygen. The hydrogens are fine, but the carbon and oxygens are having a problem. And so what you do, or what would happen, is because both carbon and oxygen have these single valence electrons, they would come together in a bond, and they would come together in the middle. And so I write this like this, where the electrons would now come in the middle here, and I would have what's called a double bond. You can actually share up to 3 groups of electrons. Whoa. So, just to rewrite it, carbon, oxygen, hydrogen, hydrogen. And so this is actually kind of a partial explanation as to why nitrogen, oxygen, fluorine, chlorine, bromine, iodine, those are all diatomic. So what I want you to do is on the bottom, let's say somewhere on the bottom, is write down O2. Draw O2. Draw this, so oxygen, one oxygen, looks like this. Another oxygen looks like this. And so what would happen is they would orientate themselves such that these guys would share, and this would share. So when you draw the Lewis dot diagram, you'd have a double bond. And so in between, I'd have the sharing of two pairs of the electrons. So that right there is a double bond. Did anybody get that? Yeah. Usually I would stop there and give you some time to do those, but I gotta move on. So we're just gonna look at structural diagrams. It's really just taking it like one step further here. Okay, so structural diagrams. Structural diagrams are the most common type of diagrams, at least that you're going to use in like Chem 30, and then we kind of have a few different types of diagrams from there. But structural diagrams represent the molecule in which covalent bonds are shown as a single, double, or triple line between atoms. So to draw the structural formula, you need to first of all figure out what the Lewis structural diagram would look like. And then wherever you have a bond, a single bond, you would put one line. A double bond, you would put two lines. A triple bond, you would put three lines. And you leave out the lone pairs. Oops, you're supposed to figure that out. But there's an example, right? pH 3. Figure that out. Okay. So let's do this. First thing I need to do is draw the Lewis dot diagram. Well, phosphorus has how many valence electrons? 5 valence electrons, and so it has a bonding capacity of 3. So that would be my central atom. So I'll put phosphorus here. 1, 2, 3, 4, 5 electrons. And then I'm going to bond my, sorry, I can't see this. 1, 2, 3, phosphorus. And then I'm just going to bond on my hydrogen. So I have 3 hydrogens, and I have 3 bonding. The bonding capacity is 3, so I've just put them into those places. So this is my Lewis formula here. Yeah, well, I mean, the thing you have to realize is all of these molecules exist in a 3D space, so they can kind of change their orientation, and then they're attracted together however you need to, right? I'm just changing them. To go from the Lewis diagram to the structural diagram, I'm just taking that, and anywhere there is a bond, a sharing of electrons, I'm going to put a line. So phosphorus is in the middle, and here's hydrogen, and we just put a single line there. They're sharing electrons. And same thing with the hydrogen below it. They are sharing electrons there, and sharing electrons right there. You do not need to include those lone pairs of electrons at the top, even though those lone pairs actually have quite a big effect on the 3D structure of them. Pardon? Okay. Is this the same ones you guys have? Yeah. Sulfur monoxide, C2H2, C2H4. Alright. I'm going to do this one. We've already looked at this one, and then I'll get you to try that one on your own. I'm actually going to do this, actually. Anyway. Okay, so sulfur monoxide. Sulfur has a bonding capacity of 2, and so does oxygen. So if I draw this sulfur, 1, 2, 3, 4, 5, 6. Oxygen looks like this. 2, 3, 4, 5, 6. So they would orientate themselves such that they do what with those electrons? Share them in a double bond, right? So, yeah, I'm just gonna, I'm essentially they're going to adjust themselves. So sulfur, and then we'd have this sharing of electrons in the middle here. So that's my Lewis diagram for sulfur monoxide. To draw the structural diagram, so sulfur monoxide, what's going to go in the middle? A double bond, so how many lines then? 2. And that would be my structural diagram for that Just got that? Okay. This one we drew before. It looked like this. Oh my goodness, what am I doing here? Alright, so we drew this Lewis diagram on the previous page. Take a second and draw out what that structural diagram would look like. What would the structural diagram look like? Sorry, the pen gets like caught on the page and then it just like jumps around. Everybody think they got it? Yeah? No? Back? Yeah? Good? Alright, so carbon, between the carbon and the hydrogens, I would just have a single bond. And then that is double bonded to the oxygen. Now in a 3D space, that's not necessarily what it would look like, but we'll look at that Monday. Alright, so, is that what everybody got? Okay. I want you, sorry, so we did this one. We did this one, we did this one. I want you to change this C2H2 and try to figure out the Lewis dot diagram. Once you have the Lewis dot diagram, try to draw the structural diagram. So first of all, we have multiple carbons. Anytime I have multiple carbons, what I want to do is bond them together. I'm always going to try and create a carbon chain. Okay, so that's what I have. And then you bonded in the hydrogens. So let's put the hydrogens here. Here, and that's all the elements I have, right? Don't start out, you know what, this just doesn't work, I better grab another random hydrogen. Well, that's not the formula. This is a formula of something that exists, so I'm asking you, how does it work then? And so, what happens is these guys end up sharing the electrons. So if you just did this for your Lewis dot diagram and said they share these electrons in what would now be a triple bond, if you left it like that, I'm happy. If you also did this, and you said that they're sharing 3 sets of electrons in here, that's fine. If your hydrogens are positioned at the top or the bottom, that's also fine. The big thing there was finding that triple bond. Now to draw the Lewis structural formula for this, I would just carbon with 1, 2, 3 lines to the hydrogen. Sort of. A little bit of problem solving. Well, right now, like, your structural diagram is fine. We're going to look at what it would see in a 3D shape, and then you'd have to draw it. Like, eventually we're looking at the 3D shape, so right now, it's fine. Yeah. I do have this example here, but I'm not going to look at that. I want to look at... Can I erase all this? You'll see something like this. NO2 negative. So that's an ion, and some people in here seem to be confused with what an ion is. An ion is a molecule that also has a charge, right? This here is indicating a charge. That's not a molecular compound. It's a polyatomic ion. Okay, so if I'm going to draw this, I'm going to have a nitrogen, 2 oxygens. What do you think this up here represents? Pardon me? Am I missing an electron? If I lose an electron, what do I become? Positive. So this probably did what then? This gained an electron. So from somewhere, outer space, I don't know, it grabs an electron and it's going to add it in. That's the last thing you want to do. The first thing I want to do is create the diagram for the nitrogens and the oxygens. So nitrogens has 3 bonding capacities, so nitrogen with 1, 2, 3, 4, 5 oxygens, or 5 electrons. I'll bond my oxygens symmetrically, so I'm going to put an oxygen here. 1, 2, 3, 4, 6, and the oxygen over here, so 1, 2, 3, 4, 5, 6. Right now, does anybody have a satisfied octet rule? No. So what could I do to at least maybe partially fix this? Connect the bottom ones. Yeah, so we're going to say these guys come together. They're going to have a double bond right there. But no matter what I do, can I form another bond for this guy right here? No. I have nothing. I have no other place to bond that. But I do have this little electron that came from, I don't know, outer space. Electron, which goes right here. So if it gives you a charge, what they're doing is they're giving you an electron that you add in to one of the orbitals to help it satisfy the octet rule. And now, oops, sorry. If I look at this, this oxygen is satisfied, the nitrogen is satisfied, and so is the other oxygen. And so the Lewis dot diagram would look like this. And this oxygen over here. And then I added in this electron. And because it's an ion, usually put it in square brackets to indicate that's an ion. The structural diagram for this would just be nitrogen, double bonded to an oxygen, single bonded to the other oxygen with that ion charge. Any questions? What time is it? Okay. So if you're leaving, you're going to finish homework 5, or sorry, homework 2 and 3. I uploaded the answers online, so if you need to double check your work, you can do that. So homework 2 and 3, because we don't have class tomorrow, this is what I would have gave you time to do tomorrow in class, so maybe during PLPs you can work on this. Okay, this is due on Monday. Okay, so if you're not going to be here after lunch, please come grab this. If you're going to be here after lunch, do the homework and then grab that. Okay, so that's homework 2 and 3, and then the review worksheet.